Hi everyone. In this last video of the lecture, I wanted to pick up where we left off in the last video. I left a couple of points on the table. One is that the SI unit for capacitance is called the farad, named after Michael Faraday. And 1 farad is a huge amount of capacitance. It's much more normal to be talking about microfarads or even picofarads in the laboratory. So most devices will be in that range. So if you're solving a problem asked for capacitance and you get 100 farads, that's probably wrong. Go back and figure it out. The other thing that I didn't mention is that the insulating material inside the capacitor has a large impact on the capacitor. It can magnify the effective capacitance by a factor of 5, 6, 7, 10, whatever, something on that order. And really what's happening is that the insulating material inside also has charges in it. And in the same way we talked about the induced charge, basically the capacitive plates induce a charge separation inside the insulator. And so next to the parallel plate, the positive charges in the insulator are attracted, and the opposite's happening. The negative charges are attracted to the positive plate. And effectively what happens is that you've created a smaller distance between the charges inside the capacitor. Now the voltage is proportional to the distance between the charges. Remember, it's the electric field, which is constant, times the distance between the charges. And so the voltage in that kind of a capacitor is less than it would be without the insulator. And because there's a smaller voltage for the same amount of charge, you have a stronger capacitor. That factor of increase is called the dielectric constant associated with the insulator. Again, it's usually on the order of 2 to 5, 6, 7, something like that. Another element that's associated with a capacitor is the potential energy. Now, this is the formula for the total amount of potential energy that's required, or the total amount of energy that's required to charge up a capacitor to a certain voltage level. And basically it's proportional to the voltage squared times the capacitor with a factor of 0.5 in there. Now this is something that we could derive from the more basic formula, which is that the potential energy is equal to charge times voltage. And recognizing the fact that there's a connection between charge and capacitance, we can figure this out. The challenge is to figure out where the factor of 1/2 comes from, and that's because as the capacitor charges up, there's more charge there. Therefore, there's more work that needs to be done to overcome or to build up more charge. And there's a little bit of an argument there for why there's a factor of 1/2. It's not critical that you follow that. Just recognize that this is the formula. This is the formula for how much potential energy is basically trapped inside a capacitor that has some charge stored in it already. The formula here is basically the energy density, and that's really just the formula on top divided by volume. And the only reason I include that here at this point is that I want to be able to refer back back to it when we talk about the energy density of the electromagnetic field and talk about electromagnetic radiation. This formula will pop up again, and basically this represents the energy density at any particular point that's due to the electric field. So we've talked in this series of videos about how the electric field basically is all throughout space. The charges, every charge that exists is exuding this electric field. That electric field actually carries a certain amount of energy content, and that is what this formula represents. The picture has nothing to do with the lecture.